Hi everyone, and today we're going to be talking about sets and function notation. Now, you might not think this is a really important thing, we're just talking about notation, which is how we write things out mathematically. But this is really important because every paper you ever read, every textbook you ever read, every equation you ever look at, there will be some notation that starts it off, and it's probably going to be some of these that you're going to see. So before we get into that, we're going to talk about some ideas of truth. So first off, we have the implication. So the implication is denoted by a forward arrow, like this, and essentially all it's saying is if A is true, then B is true. There's also a bijection. So it's denoted by an arrow pointing both directions, and this is often written out as if and only if, or sometimes you'll see it as IFF. And this is saying if A is true, then B is also true, and if B is true, then A is also true. We're going to show this a little bit more detail when we talk about sets, but just keep this notation in mind. So now getting into sets. So to start off, a set is essentially a collection of objects, and each object in the set is called an element. So here at the bottom we have some set A, which is denoted by a capital letter. We'll use capital letters to denote sets, and usually lowercase letters to denote the elements in those sets. So A has 5 different elements, and they're just numbers, 1, 5, 7, 9, 12. You can put whatever you want into sets, but usually we're going to focus on numbers just because of robotics. Next we have the cardinality of a set, and the cardinality of a set is denoted by 2 bars around the actual set. So if you ever see this notation, that just means the number of elements in a set. So you can see at the bottom we have a set A, 1, 5, 7, 9, 12, and it has a cardinality of 5. So here we have the notation to note whether something is in a set or not in a set. So if you see this symbol, it means that it is a member of that set, and if this symbol, it is not a member of that set. So we have X as some member of some set X, and we have our set A here at the bottom, and 1 is a member of A, and 2 is not a member of A. So next we have some special sets. These are really important sets that will show up a lot. So the first one is the null set, or the empty set, and this just represents a set with no elements in it. There's a lot of properties with this that we're not really going to go into because we oftentimes don't really need to, the way we're defining things in the real world, but keep this in mind. There's also the set of all integers represented by this Z here, and then you also have Z plus, which is the set of all positive integers. Then you have R, which is the set of all real numbers. We're going to use these a lot when we define like state vectors, or measurements, or really any value in our robotics system. They're usually going to be made up of some set of real values or some integers. So next we have for all. So this notation essentially denotes that something is true for every element in our set. So what we have here is for all X that belong to set of all positive integers, we know that X is greater than 0. Because if we look at the set of all positive integers, it goes 1, 2, 3, all the way going out to infinity. All of those are greater than 0. That property holds for all of them. And a lot of times you'll see things like, for all states in our state space, this must be true. And this is kind of where this notation comes from. So next we have there exists. So this just means that there's a single element for which this is true. So this would be read as, there exists an X in the set of integers such that that X is 0. And that does not mean this property needs to hold true through all of them, or even any except for 1. If one element has this property, this statement is true. So you're going to see a lot of things like there exists some initial state. So next we're going to talk about the complement. So we have A, essentially what looks like the power of lowercase c. So there's a c in the superscript, and this is the complement. And essentially what that means is anything that is not in A is in the complement of A. Now usually we're going to define some domain over which this is true. And that's going to be denoted by a thing called omega here. So essentially if we have omega, which is the values 1, 2, 3, 4, 5, this is essentially all the possible values that could be in a set. So A would be 1, 2, 5, omega would be 1, 2, 3, 4, 5, and then A complement would be 3, 4, because it's every element that is in omega that is also not in A. So next we have the union operator, and this is a good way to combine 2 sets. So let's say we have some element A from some set A, and some element B from some set B. We can define a new set D, which is the union of A and B. And then essentially what that means is every element in A is in D, and every element in B is also in D. So that means for all elements that are in my D, that D is either in A or is in B. So you can see the union at the bottom. So if we have 1, 2, 3, and then B is 2, 3, 4, well, we end up with a set of 1, 2, 3, 4. Every element in A is in the union, and every element in B is in the union, and there's no duplicates. So if something is in both A and B, you don't include it twice in the set. Every element in the set must be unique. So next we have the intersection operator, and the intersection operator defines essentially what are the common elements between two sets A and B. So we have an element A and A, an element B and B. That element is only in the intersection if it is in both. So essentially that means for every element in our set D that combines the two, we have that D is in A and that D is in B. So we have at the bottom, we have A is 1, 2, 3, and B is 2, 3, 4. The only common elements are 2 and 3. 1 and 4 are not in both sets, so they're not in the intersection. So next we have subset, a set contained in another set. So if we have A is a subset of B, that means for every element in A, that element is also in B, but B can also contain elements that are not in A. So if we have, as we define down here, we have A is 2, 3, and we have B is 2, 3, 4. We can see that A is a subset of B because it has every element in A is also in B. That does not mean that every element in B is also in A. So next we're going to talk about sets of vectors and matrices. So this is the most common notation you'll see pretty much in any paper you pop up. It will almost immediately define what its state space is, or what controls it's using, or where this robot is operating, and that is usually done through these kind of notations. So we have like X is a vector in Rn, or X is a vector in Rn cross n. And what you're seeing here is, so A is 2 by 3. So this is some matrix of 2 by 3 where each element is a real number. Or you have some X transpose belongs to R3. So you have X written out. So X is just a vector of length 3 with 3 elements, and all of them are real numbers. So next we have function notation. And this is going to essentially what allows us to define things that operate on some set of values. So we're going to take in some variable and we're going to output some variable. So this is typically like read as F is a mapping from A to B. So A is where it starts, and you have the arrow which pointing to B, which is where it ends. So a lot of times you'll see things like this. You have some vector X that belongs to Rn, and then you have some F which operates on X, and that is a mapping from Rn to Rm. And if we write out our function as Y is equal to F of X, that implies that Y belongs to Rm. So this is how everything will be defined with respect to robotics, especially in papers. They'll write out some, like, we have some state vector, we have some controls that we have, we're going to do stuff with them, and then the output is going to be our new state. And they're going to write it in this notation. So you can also have functions with multiple inputs, and you get notation that looks like this. So you have some function h, which is a mapping from Rn, Rk to Rm. So you put in your two variables here, you have your colon, and then you have whatever one vector is cross the other vector, outputs another vector. So you can see here we have the same thing at the bottom. So if x belongs to Rn and z belongs to Rk, we take y is equal to h of x comma z. That implies that y belongs to Rm. So next we're going to talk about this really common notation you'll see in papers. So we're going to define a set based on some output of a function. So what this is saying is I have some function f which maps from Rn to R. So I'm going to get a real value out if I put in a vector. And then we're going to define some set in which every element of that set has this property that is true. And the way we're going to write this out is we have some set capital X, which is equal to some X, and this line typically denotes something like such that, or where, for every X belongs to Rn. So that means that I'm going to take every possible vector X, and then I'm going to pass it through this function f, and if I get out a positive value, that element will be part of my set, and if I get out a negative value, it won't. This does not mean that every element in this set of Rn has this property, just every element that I'm including in my set capital X does. And there's two different ways that people tend to write this out, which I've written below, so try not to get tripped up on different notation. So overall, we looked at sets and see how important sets are in defining different values that we're going to use in robotics. The really important property of sets is they allow us to talk about a family of objects rather than a single value. And often we will define sets based on some property, like we talked about earlier. Now, the reason we cover this so specifically, and it might sound pedantic, but this notation is ubiquitous. You will see it in every paper you pop open. So the goal with this video is to show you the notation so that when you get there, your eyes don't immediately glaze over. You can go, oh, I've seen this before, and start parsing through what you're looking at.